Hello and welcome to Team 27's final presentation. Our team members are Holden Collins, Benjamin D'Angelo, Arjun Ganesh, Tyler Jens, and Dylan Rich. We have selected to do our project on the analysis and redesign of a manual drill driver. While manual drill drivers have largely been replaced by the electronic equivalent, they still have many use cases. For example, they are useful for performing operations where control is prioritized over speed, such as drilling very small holes in wood. Also, since they don't require electricity, they can be used in places where it's difficult to keep charged batteries. Here, we have the CAD model of the assembly and the CAD model in an exploded view. For this project, we consider the keyless drill chuck to be a single off-the-shelf subassembly. From our market research, we found many similar manual drills available for sale, which indicates there is a demand. Although we estimate production volume to be relatively low for mass production at 50,000 per year, our primary customers include professional and hobbyist woodworkers who use the tool for their work. Our secondary customers include painters who might use a mixing attachment instead of a drill, and other various DIY tasks. The woodworking consumers and DIY customers are both using the same tool but have slightly different needs. For example, the woodworking customers are looking primarily for durability, ergonomic design, and precision in their manual hand drill. On the other hand, the DIY customers are more likely looking for versatility and simplicity instead.
Next, here is the fast diagram, showing the functions of the manual drill. Since we consider that the product may be used to drive tools other than twist drills or drill bits, the primary function is to rotate the attachment. The function component mapping matrix here shows the functions performed by each component. Since the assembly has 3 gears, many components serve to transfer power through torque and speed changes. Additionally, this function component mapping matrix serves to show many similarities in functions of the parts. For example, the bolt and nut both have the exact same functionalities, which may be an opportunity to improve in the design. As shown earlier, the 2 different consumer groups have different needs, and therefore have slight differences in functionality preferences, which is identified here by this functional differentiation table. These functions can then be specified into the specific module parts that will create the differences between the groups. Here is our initial assembly sequence, followed by the assembly sequence with delayed differentiation for assembling different products. This is the sequence followed when determining the manual and automated assembly times. To further assist our redesign decisions, we made a quad chart classification for all the parts in the overall assembly, ranking them by their importance and cost. The parts that were most important at the lowest cost were the main handle and the crank handle. We discussed earlier that the chuck is a module within this product, enabling various functionalities through swappable components. Here you can see the CAD for each of the modules and primary interfaces. The hand drill has various chuck attachments to assist with a variety of user needs. This slide gives a bit better representation of how these chucks attach onto the spindle. Each has their own attachment sizes, suitable for a diverse breadth of applications.
Next, the manual assembly time was calculated by analyzing the highest impact parts. The slowest part was the body, with the chuck not far behind. The spindle and all of the handles also take up a pretty big chunk of time, leaving room for improvement. However, even though the body and the chuck would improve manual assembly, they have a high cost as seen in the quad chart. Some other difficulties include complex geometries, precise tolerances, and threading. Now, here's one modification that includes a part consolidation of the side handle and side handle ferrule. This new part can have improved symmetry by making the attachments for the spindle and the hand pin the same. Finally, there were added chamfers for easier insertion of the spindle and handle pin. Functionality-wise, there were no changes made. However, the manufacturing costs will likely increase. Another modification is to make manual assembly of the chuck easier by adding chamfers for easy insertion, adding knurling to make the chuck easier to screw into spindle threads, and avoiding adjustment to the chuck by temporarily locking during packaging. Next, we analyzed the automated assembly cost of some of the parts of the drill assembly and chose to modify the crank plate due to the fact that it has the highest cost in its existing state. For the crank plate and side handle, we reduced complexity by combining the handle and side handle ferrule, and also reduced the number of fasteners by swapping the nut and bolt with a rivet. For the crank plate, we increased part symmetry by moving the side holes to be the same and equidistant from the center. The first part we chose to redesign for manufacturing was the crank handle. The key dimension for this part is the inner diameter, which attaches the handle to the crank plate through a rivet. The handle will be plastic for comfort, so we selected injection molding as the process for this part. The second part was the crank plate. The key dimension for this part is the distance between holes, which determines the speed and torque transfer, which are important functions of the product. Because of this and the small and varying cross-section of the part, we selected machining as the manufacturing process.
Analyzing the crank handle, DfM Pro gave 3 suggestions. First, the hole for attachment lacks a draft angle, which should be at least 0.5 degrees. Next, the part wall thickness varies and should be consistent as possible to prevent voids. Finally, the mold wall thickness is small in some areas and should be increased to improve durability. Analyzing the crank plate with DfM Pro, it was recommended that the center hole diameter should be changed to a standard drill size, either 189 or 191 thousandths. Taking these suggestions into account, the crank handle was redesigned to have the required draft angle. It was made hollow to maintain a uniform wall thickness and widened slightly to ensure the mold thickness is not too small. This greatly improved the cost per part. Changing the center hole diameter of the crank plate slightly reduced the cost per part according to Hubs. To summarize the changes we made, we don't think that reducing the part counts and changing the impacted part geometries will significantly impact the customer experience. The most significant impact is likely to be the change in the geometry of the crank plate, which may give the user less power when drilling through tough woods, but shouldn't be impactful in most cases since the bevel size hasn't changed. The simplification of the assembly and reduction in part count should result in fewer breakages and therefore greater reliability, which should be appealing to customers, and the handle designs remain ergonomic. As for the impact of changes to the overall manufacturing process, the reduction in parts and materials should simplify sourcing and the supply chain, and the elimination of wood parts should mean it's more environmentally friendly. Finally, the reduction in parts and increased manufacturability should make the product cheaper to produce.